What you're looking at is 3I Atlas, captured with a 16-inch Dobsonian telescope and processed using a Larson Sekanina filter. That filter matters, so let's get that clear first. It removes anything that's smooth and circular around the core. In other words, it strips away the general glow and forces directional structure to stand out. So this image isn't about beauty, it's about geometry. At the center, you can see a bright, elongated core region marked as 3I. From that core, material extends in a clearly preferred direction, not evenly in all directions. That's the key point. If this were just random activity or noise, you'd expect a messy, symmetric blur after this kind of processing. Instead, what remains is organized. You can also see that this structure lines up relative to the solar direction, marked at 310 degrees. That gives us a fixed reference frame. This isn't something floating randomly on the detector. Now look at the background. It's chaotic. Stars, noise, residuals everywhere. The filter doesn't clean those up nicely at all. Yet the structure around 3I Atlas still survives. That tells us something important. Whatever is happening near the core is stronger and more coherent than the background clutter. What this image does not tell us is what the object is made of. It does not tell us the cause of the outflow. What it does tell us is simpler and more solid. There is directional activity tied to a specific orientation in space, and it's strong enough to remain visible after aggressive processing. That alone makes this image worth paying attention to. What changed from the first image? This is the same target, the same observation session, the same solar reference at 310 degrees. What's different is the contrast and the stretch. Here, the background has been pushed flatter, and the central region has been emphasized. That allows weaker structure to show up without the core completely blowing out the frame. This isn't adding new information, it's isolating what was already there. What stands out now is a clearly defined, localized bright core, with a diffuse but directional extension trailing away from it. And the important part is the shape. It's not circular. It's not evenly smeared. It has a preferred axis. And that axis stays consistent with what we saw in the first image. That consistency matters more than the brightness. Now, look at the solar direction marker. The arrow gives us orientation. When you line it up with the extended structure, you can see that the outflow is not random with respect to the sun. This tells us the geometry is doing real work here. The object is interacting with its environment in a way that produces repeatable directionality. That's the key word, repeatable. So what does this image add? Compared to image 1, this view confirms the structure isn't a processing artifact. It shows the extension survives different stretches, and it reinforces that the activity is anchored to the core, not drifting in the background. In short, image 1 hints at organization. Image 2 confirms it. What this image still doesn't claim is the mechanism behind the activity. It doesn't tell us how many sources there are, or whether they're steady. What it does tell us is simpler and solid. Whatever is happening near the core is directional, persistent, and geometrically constrained. And that sets the stage for the next image, where structure stops being subtle and starts becoming unavoidable. What's different here? This is the most aggressively processed view so far. The Larson Sekanina filtering is pushed hard, and the color scale is doing real work now. Bright regions are no longer about brightness alone. They're about contrast relative to rotation. Anything that's smooth gets suppressed. Anything that changes with angle survives. What immediately stands out is that the core region is no longer just elongated. It's surrounded by distinct, uneven structure. You can see a bright central region, dark gaps around it, and multiple lobes emerging at different angles. This is no longer a single directional extension. This is structured activity, broken into components. Why does this matter? Random noise does not organize itself into angular patterns centered on a core. Background stars don't do this either, especially after this kind of filtering. What you're seeing here is something that rotates with the object. It changes with angle, and it remains anchored to the same central point. That's the key takeaway. Now connect all three images. Image 1 showed direction. Image 2 confirmed persistence. Image 3 exposes internal structure. Not just something extending outward, but how it's distributed around the core. This progression matters because each step uses a different stretch or filter, yet the geometry keeps reappearing. That consistency across processing levels is hard to ignore. What this image still doesn't claim is how many sources there are. It doesn't tell us whether these features are steady or intermittent. But it does tell us this: whatever is driving the activity is not uniform, not chaotic, and not an artifact of one processing choice. At this point, the structure is doing the talking. What you're looking at are two Hubble observations of 3I Atlas, taken on November 30th, 2025, separated by just 23 minutes. Same instrument, same target, almost no time gap. That's what makes this powerful. The overlaid lines mark measured position angles of distinct outflow features, all referenced to north, east, and the projected rotation axis. This isn't interpretation by eye. This is measured geometry. Now look closely at the two panels. The core stays put. The background stays noisy and random. But the directions of the outflow features shift. Not dramatically, not chaotically, just enough to measure. That shift is the entire point. Why does this matter? Nothing large-scale should noticeably change in 23 minutes unless it's tied to rotation or anchored to a body that's turning. The angles marked here don't jump around randomly. They pivot around a common axis. That tells us the structure we saw in the ground-based images isn't frozen in place. It's moving with the object itself. So what's the key takeaway from Hubble? From these two frames, researchers infer a periodic wobble of the outflow system with a time scale of about 7.2 hours. That number doesn't come from guessing. It comes from tracking how these angles evolve. This is the first time in this sequence that we're not just seeing structure, we're seeing motion. Now connect this to the earlier images. The Dobsonian observations showed direction. They confirmed persistence. They revealed internal structure. Hubble adds something new: timing, repeatable angular change, rotation-linked behavior, different instruments, different scales, same underlying geometry. That consistency is the through line. What this still doesn't say is what's causing the outflow. It doesn't tell us how many sources are involved, but it does tell us this: whatever is happening is organized, rotationally linked, and stable enough to track over time. And that narrows the field of explanations significantly.
What you're looking at is a Hubble brightness map from January 14, 2026, processed with a Larson Sekanina rotational gradient. That processing step matters more here than anywhere else. It deliberately removes anything that's smooth and symmetric around the core. What survives are features that break symmetry and change with rotation. So what you're seeing is not raw brightness. It's structure, isolated by motion and geometry. What stands out immediately is a compact core with multiple narrow outflows emerging from it. Not one, not two, 3 small jets spaced almost evenly around the core, plus a longer extension in the sunward direction. That spacing is the key detail. When features are nearly equally separated in angle, that tells you they're likely tied to fixed regions on a rotating body, not random release events. Why isn't this just a visual effect? Larson Sekanina filtering is brutal. It erases anything that doesn't rotate coherently. So the fact that these features remain means they persist over rotation. They're anchored to the core. And they repeat in the same angular positions. Noise doesn't do that. Background doesn't do that. Artifacts don't do that consistently across instruments and dates. Now rewind mentally. Ground-based images showed directional activity. Stronger filtering revealed internal structure. Hubble timing showed angular motion. This map shows stable angular spacing. Different nights, different telescopes, different processing, same underlying geometry. That's the through line. So what does this image actually tell us? It doesn't explain the mechanism. It doesn't tell us the composition. It doesn't tell us why these regions exist. What it does tell us is simpler and harder to dismiss. The activity around 3I Atlas is organized, rotationally linked, and persistent over time. That's it. No leap beyond the data. And this is why it matters. When structure survives aggressive filtering, multiple viewing geometries, and independent instruments, it stops being something you can wave away as processing tricks or chance alignment. At this point, the images aren't asking us to speculate. They're asking us to pay attention. So where does that leave us? Across different nights, different instruments, and very different processing methods, the same geometry keeps reappearing. Not once, not twice, but consistently. The images don't tell us what's causing the activity. They don't tell us why these regions exist. But they do tell us something harder to ignore. Whatever is happening around 3I Atlas is organized, rotationally linked, and persistent over time. The real question now isn't what we think this object is. It's what future observations will confirm or rule out. As new data comes in, will this structure hold? Or will it break down under closer scrutiny? That's the part worth watching. If you want to follow how this unfolds, consider subscribing. And if you have your own take on what these images show, leave it in the comments. We'll keep tracking the data as it comes in.